Okay, thanks for the introduction. My name is Dae-hyuk Kim. I'm a PhD student at CMU. Today I'm going to talk about our ongoing work on enabling memory-intensive network functions on programmable switches with an external memory abstractions. This is a joint work with Microsoft, Barefoot Networks, and my advisors, Vyas and Srini. Today's data center network, they're widely deployed merchant silicon switches because they're cheap and widely produced. However, they have very limited memory space, which is typically tens of megabytes. Now I explain how such limitation can be a key bottleneck for memory-intensive network applications using an example called bare metal hosting service in the cloud. In this service, customers can install their bare metal servers to public cloud, and the cloud providers need to provide a virtual switching between the bare metal servers and their VMs. You know that the network virtualization have been relying on software switches on hypervisors, and hypervisor switches can use enormous amount of DRAM on host servers. However, in bare metal service, you cannot trust the bare metal servers, so you cannot install any component in the servers. So the only available solution is to move the virtual switching functionality to Tor switches. Unfortunately, Tor switches only have limited SRAM space that's not enough for storing all virtual switching table. So how do you solve this problem? This example illustrates that the limited memory space is a bottleneck for memory-intensive network functions or applications. One natural solution would be to add more DRAM on the switching board. In fact, some expensive fixed function merchant silicon chips are built and designed to be able to take advantage of external DRAM. Such chips access external DRAM located on the same switching board through numerous DRAM modules and controllers installed within the chip. However, this approach is very limited, so not that useful in practice. The memory can be used only for a few specific functions, which is chosen at the chip design time. The total amount of DRAM you can put is also fixed at the chip design time. Also, it's expensive because the chip gets larger and complex due to additional wires and modules. So our question here is it possible to extend switch memory by leveraging available resources on other devices in the data center? We have observed some opportunities in data centers by analyzing some resource traces from production clusters. The first observation is that servers' DRAM are mostly underutilized. For example, this graph shows memory utilization of a server in Google's data center during 5 days. You can see that the median usage is around 50%, and most loaded cases around 80%. You also observe the similar usage pattern in Alibaba's cluster trace. The second observation is network link bandwidth in data center is also underutilized. Recent measurement study from Facebook shows the utilization of link bandwidth between the Tor switch and the servers is around 1% on average and 10% in mostly loaded case. So our question was, can you leverage such underutilized resources for extending programmable switches memory capacity? Based on this observation, we proposed GEM, generic external memory for the programmable switch data planes. In GEM, instead of attaching separate DRAM to the switching board, we actually decide to reuse existing resources in data center. The key advantage of our approach is that it's very cheap, flexible, and readily available. It just reuses existing commodity hardwares in data centers without adding additional infrastructure cost. Also in GEM, you can adjust an amount of DRAM and the link memory access bandwidth at runtime. Essentially, GEM introduces the notion of memory hierarchy to programmable switches. So you can use on-chip SRAM as a cache and remote DRAM as a main memory, just like in memory hierarchy in CPU architecture. In this work, we are particularly focusing on applying our idea for memory-intensive network functions in data centers. So how can you realize this vision? Specifically, we need to solve three key problems. Suppose that the switching chip can use remote memory using GEM architecture. When the lookup miss happens, the chip will try to look up a remote table. For this, we need an access channel that allows the data plane to directly access remote memory at low latency. Also, if we want to modify the packet based on the remote content, the data plane may need to keep the packet until it gets a remote table entry. Lastly, we need remote lookup table and corresponding APIs so that the data plane can use the remote table just like as a local data structure. So how to enable the switch data plane to directly access remote memory? In particular, it has to access purely DRAM, making no impact to other compute or networking workload on the servers. Also, it needs to achieve minimal latency between the chip and external memory. But there's no obvious way to connect the chip and memory directly. The chip only has Ethernet as an external interface, and DRAM has only DDR as its external interface. To enable DRAM access from the chip, we need to somehow translate Ethernet directly into DDR interface. Fortunately, we already have such technology. It's called RDMA, or Remote Direct Memory Access. A RDMA NIC on server can receive and process RDMA requests from generated by the switches and send response back to switch without CPU involvement on the server. And a good thing is many data centers already have deployed RDMA NICs on their servers, so we can just reuse them. Here, the key challenge here is generating RDMA request from the data plane. Since the programmable switches chip cannot generate arbitrarily new packet from the data plane. So how can you solve this problem? Since the switch data plane cannot generate arbitrarily new packets, we decided to reuse incoming packets that triggered remote memory access. So to generate RDMA requests, we replicate an incoming packet and add RDMA headers on top of it. Then the RDMA read request will fetch the content from the remote table. Also, to manage the reliable RDMA connection with RDMA remote servers, we let the data plane to maintain a minimal set of RDMA connection state, including queue pair number, packet sequence numbers. And the good thing is all these features can be implemented in P4 language. Now, the switch data plane can access remote memory via RDMA channel. Then how can we manage the packet during external memory access? Now, while the switching chip can issue RDMA request, here's a potential problem. What if the data plane needs to modify the packet based on the content fetched from the remote memory? For example, in that case, IP address and port field need to be changed. A strawman solution would be buffering a packet until it receives a RDMA response from the remote memory. However, buffering a packet can consume a large amount of SRAM space and cause other issues such as pipeline stall and packet drops. To solve this problem, we propose a simple but effective solution. Before sending a RDMA read request, we first store the incoming packet to remote table, remote memory, and then read both the table entry and packet back together. This way, the data plane can modify a packet with the remote table entry without using additional SRAM space. The last component is lookup table data structures in remote memory and APIs for accessing it. In this example, to look up an entry from the remote lookup table, the data plane needs to know the remote memory address corresponding to the key. One straightforward solution would be to store a mapping between all possible keys and remote memory addresses on on-chip SRAM space. However, again, it would consume a huge amount of SRAM space, which is undesirable. So how can we effectively realize lookup table on remote memory and support the operations such as lookup and update without consuming lots of SRAM space and without accessing remote memory multiple times? To solve this problem, we designed GEM lookup table data structure. GEM lookup table is a variant of two-way cuckoo hash table. And although a standard cuckoo hash table requires at most 2 memory access for lookup, our lookup table guarantees a single memory access per lookup. The key idea is to maintain a summary of a cuckoo table on SRAM using a balloon filter instead of the whole mapping. So for a given key, such as 5 tuple of the packet, this summary tells you which table contains the key so that the data plane can access the table without multiple DRAM access. Based on this, we provide a key value table abstractions to data plane applications. Let me explain it using the same example. When a table miss happens, it first asks balloon filter about which hash function was used when storing this key. In this case, since the key was hashed by H1, the first hash function, the address reserver calculates the remote memory address based on the H1 value of the key. And then the data plane can issue RDMA request based on this address. So far, we have looked at our design with the single server case. While the single server design allows accessing to remote memory, it cannot scale to support demands that exceeds available DRAM capacity of the single server or access bandwidth with a single link. To address this, we extend our design to scale GEM to multiple DRAM servers using a combination of sharding, replication, and caching. Due to the time limit, I'll skip the detail in this talk, but we can chat in offline. We have implemented a prototype system using a Tofino-based programmable switch and 8 servers with RDMA-capable NICs. And here are some key results. In that case, we observed GEM incurs less than 3 microseconds end-to-end latency overhead due to external memory access. For lookup throughput, with a single server with caching, GEM can achieve 20 millionths lookup per second. But the lookup throughput can be scaled as we added more servers. For example, with 4 servers, it can achieve nearly line rate even without caching. Overall, limited memory space on programmable switches is problematic for memory-intensive network functions. To solve this problem, we propose new generic memory architecture for programmable switches, which is cost-efficient, flexible, and scalable. GEM provides an external memory abstractions for programmable switches, and developers can use the abstraction for different, to develop different kinds of memory-intensive applications. With that, I'm happy to take any questions. Thank you.
Question there?
Yes, on your solution to C1, realize we
You would like to also summarize the question?
Yeah, let me check. So your question is, when the switch issued the RDMA request,
The monitor,
what happens to that incoming packet, right?
You're running on the switch, you realize that you will be remote memory access. At that point, you said you clone the packet, you stick it in RDO data.
Right.
All right, at that point, that clone packet, what? It's jammed going to the receive queue, and you're basically going to restart the processing of that packet, or does something else happen?
I see. So what happens here is once you clone the packet, it generates, so in this case, let me show you. So it clones the original packet into two replicated packets and add RDMA header for create RDMA write and RDMA read request. And this read response packet, it contains both original packet and the remote table entry. And then when the data plane receives this read response packet, it can parse the original packet and the remote memory entry. So it will apply the remote, like for instance, it'll modify the destination IP address with this action field entry.
Are we still sitting there? Are we still sitting there with the original packet
Yeah.
on the programmable switch waiting for this processing to happen?
so the question is, what happened to the original packet?
What?
What happened to the original packet, he's asking.
So original packet is first stored to the remote memory. So there's no stalled packet in this pipeline, the programmable switches.
All right, we're not buffering it
Yeah.
And picking it up later or something.
Right.
Okay, thank you.
Question on that side?
It looks like you're recirculating the packet. It looks like you're sending it out and sending it back in. So even if it's happening at line rate, doesn't this mean you're sort of using twice as much of your switching bandwidth?
So we are not recirculating packet. We just clone the packet and to generate the RDMA request and put the original packet to the remote memory.
But the packet will come in
Yeah, we're
again.
coming back again.
Instead of just going through the switch, it has to go out, back in, and then through, which means that it's using twice your switching bandwidth.
Yeah.
It has to be, yeah. So even though it's line rate, it's still kind of, you're doubling your resources.
Right. So to achieve the line rate, we need to extend our link bandwidth.
Okay, I have a question. Generally, RDMA requires a reliable transport.
Sorry? The
RDMA requires a reliable transport
Yeah,
to be really healthy.
Right.
Like, what's your read? If your read fails, what do? Do you time out? I mean, this question. So how do you handle an absence of reliable transport in this case?
So we are in the data plane.
I think we lost the slides again.
So we maintain a minimal set of the connection state, such as QPR number and packet sequence number, so that we can use it to retransmit. I mean, when the connection becomes invalid for some reason, we can use such information to retransmit the packet using the previous sequence number. From the data plane. Yeah.
More questions? Thank you.